All right, so our first one, 12.0 millimeters times 6. This gives us what? So you punch this into the calculator, you type in 12 times 6, and it spits out 72, right? But we have 3 significant figures, so we should have 3 significant figures in our answer. So we should have 72.0 millimeters, or you can put it in scientific notation, 7.20 times 10 to the 1 millimeters. Or if you want to convert this into meters, you could have 7.2 times 10 to the minus 2 I'm sorry, 7.20 times 10 to the minus 2 meters. All of these are accurate or correct. Is it okay? Are we feeling okay about?
There's 3 significant.
Yeah, there's 3 significant digits, right? So we got 3 significant digits. But I guess I just also want to make sure we're okay with the metric system, going from meters to millimeters and back and forth. All of that stuff. How many millimeters in a kilometer? 10 to the 6, so 1 million. 1 million, yeah. Good. Okay, 12 millimeters times 12 millimeters. So we've got 2 measurements. So you punch 12 times 12 in your calculator and you get 144, okay? But we only have 2 significant digits here and we only have 2 significant digits here, so we should only have 2 significant digits in our answer. So we should write 140 millimeters squared, or to accurately report this or make it non-ambiguous, you can write 1.4 times 10 to the 1, I'm sorry, 10 to the 2 millimeters squared. So 1.4 times 10 to the 2 millimeters squared. Converting it into square meters gets complicated. Maybe I'll save that for a later step. Does anyone know how many square millimeters are in a square meter? So meters to square, I'm sorry, millimeters to meters, there's 1,000 millimeters to a meter. But then for square millimeters to square meters, you have to do 1,000 times 1,000. So there's actually 10 to the 6 millimeters square in 1 square meter. And I'll show you the conversion in a moment here. Okay. This is okay? So 1.4, only 2 significant digits. Okay, what do we have here? We have 3 significant and 3 significant. So we punch this into our calculator, we get 144 times 4. So 144 times 4, I didn't actually do this. 576. And so that's okay, right? 576 square millimeters, or 5.76 times 10 to the 2 millimeters square. Have I lost anyone yet? Not yet. Okay. All right, so this last one. Okay, we'll punch this into the calculator. We get 12 times 12.01 times 3, and we get 432.36 in the calculator, okay? But we only have 2 significant digits here. We have 4 significant digits here, okay? And the ones, the they don't count. Okay, so we have to go down to 2 significant digits. So we would have 430 millimeters squared, or 4.3 times 10 to the 2 millimeters squared. Okay, so even though we have 4 digits over here, we got a really precise answer over here, but this one only has 2 significant digits. So we essentially have to throw away the extra precision that we got over here because this one is imprecise.
That's your potato example.
This is our potato, yeah. This is our bag of potatoes. Because this has imprecision, we cannot report an answer that's more precise than this.
That makes it.
Yeah. Okay. So, this, again, it only comes into play when we're dealing with measurements, right? If somebody just says, what's 8 times 8, you don't have to say 60, okay? You say 64, okay? 8 times 8 is 64. But when you're dealing with measurements with imprecision, you have to take that into account. Now, probably in most day-to-day life situations, you're not going to be thinking about, oh, did I mess that up? Shoot. I think I messed something up. You're not going to be thinking about significant digits or things like that. And you probably don't have to worry about it on a day-to-day setting. But in a lab setting or in a clinical setting, these measurements and the significant digits do matter. Again, the idea being we don't want to report more accuracy than what we should, or more precision than what we should. Okay, let's do some significance rules with addition. Okay, so the idea with significance rules over here with addition is that your final answer cannot have more decimal places. So not significant digits, but decimal places than the measurement with the fewest decimal places. Okay. So let's see. All right, and let's see, we have something like this. Okay, so let's say this is 1 centimeter and this is 2 centimeters. How long is this stick? This thing. You just have to guess, right? 0.8, So I would say 0.8 centimeters, okay? I don't know. All right, and let's say I take another thing. that is this long.
Yes.
Yeah, and you got to just another guess here. 0.7, sure. Okay. Obviously, there's uncertainty in these measurements, okay? So if I add these two together, add 0.8 centimeters plus 0.7 centimeters, my final answer will be 1.5 centimeters. Okay? And is that okay? What is our rule? So we're dealing with decimal places, okay? So here, I don't have to worry about I've got one significant digit and one significant digit, but I don't have to turn this into just one significant digit, okay? This is with decimal places. So I've got one spot behind the decimal, one spot behind the decimal, so I'm allowed to have one spot behind the decimal here, okay? And so this is my answer, 1.5 centimeters. Okay.
Can we do that? Let's say it's 0.7 is 0.68. Then
Yes, yes. Okay, so let's say somehow, we got another piece over here, and this one we got measured very accurately. I don't know, one. Yeah, I don't know what I'm doing here, but so we measured this, and yeah, let's say this is we got this piece to be point. This is 0, 1, and this is 5, so 0.62 centimeters. Okay, so this one is 0.62 centimeters. But this one is still 0.8 centimeters. So if I took this piece and I added it to this one, so we have 0.8 centimeters plus 0.62 centimeters. What is my end result here? Yeah, so when I punch it into the calculator, I get 1.42 centimeters, but we are only allowed to have one decimal place. One decimal. Over here I have two decimal places. So our final answer can have only one decimal place, and that will be 1.4 centimeters. So again, the idea here being, if this is our bag of potatoes, we can't be more accurate, even if I know I'm going to add on a piece that's exactly a certain thing, 0.62 centimeters. I've got something more accurate over here, because this last digit is basically eyeballed or guessed. We have to take that uncertainty into account, and we shouldn't have more decimals in the next step. Okay. We okay? So we'll try a few addition practice problems. Addition and subtraction practice problems. So we'll say 31.4 milliliters minus 10.26 milliliters. Oh, shoot, now I'm confusing myself here. You know what, let me just change this to 1.0 liters, sorry. Okay. You guys need another minute, or are we doing okay? We're good? Okay, so let's see what we got. 31.4 minus 10.26. If I punch that into the calculator, I get 21.14 milliliters. Now, I'm allowed to have up to one decimal place. So I would say 21.1 milliliters. Okay, one decimal. Okay, 31 plus 3.617. If I punch that in, I would get 34.617 milliliters. And so I have no decimal places, so I have to go to what? 35 milliliters. I'm sorry?
You rounded it up.
Should I round it down?
I don't know. Why not just make it
No. So the rounding rules is that the number that comes, if the number that comes after the spot that you're rounding to, so I'm rounding up to the ones place, right? So the if I'm rounding, whatever number comes here, if it's 5 or higher, we go to the next number up. 4 or lower, we go down. So this is a 6, it's bigger than 5, so we round up to 35.
That's one on the right of the decimal. You have none on 31, so you.
Correct.
34.
So I'm rounding off to the ones place. So I'm just rounding off to the decimal. So I'm not going to have anything after the decimal.
Okay.
So I look at that number.
But that's not accurate. Why do you look at that?
Well, because so I have to decide whether I should report 34 or 35. Okay? And so right now my best guess or my best estimate is to look at this number and make a decision. Okay? Because this 31 could really be anything between 30.5 to 31.49. Okay? And so when I take this into account, the number that I should get is going to be 35. Or we can do a few more practice problems just to make sure. Okay? So here, I made it a little tricky. 1.0 liters plus 112.2 milliliters. So what do we do? So we got to put it all on the same unit. Okay? So whenever you're dealing with multiple unit type things, you should all convert them into the largest unit that you have. Okay? So I have 1.0 liters, and what is 112.2 milliliters in liters? It would be 0.1122 liters. Okay? And so if I add these two together, I would get 1.1122 liters. I am allowed up to 1 decimal place, so I would have 1.1 liters. Okay. Did we do okay? Kind of? Maybe I guess we could practice rounding.
No, it's just a regular rounding.
Yeah. Okay. Has anyone in any of the other like sciencey stuff talked about I don't know what the round to even rule or banker's rounding? No? Okay, we won't worry about it then. Okay.
I understand that. I just thought we couldn't use that digit.
You can't use that digit in your final answer. Okay, you don't want to report that, but you want to take that into account when you give your final answer. Okay, is it better to say, yeah, so if someone says, oh, he's got like $3 million or something like that, and that's just kind of maybe it's not completely accurate, but it's a good idea. $3 million. I'm sure it's not exactly 3 million. And someone says, oh, he got a gift of 700,000. It's not quite $1 million, but 700,000, and you add that to him. Would you then say, oh, his net worth or total worth is still 3 million, or should you say, well, it's probably closer to 4 million now? And you would say it's closer to 4 million now. So that's basically what we're doing. We're rounding, but we're taking into that that last digit that we've got. Okay. Let's see. Okay, so let's put this all together in what's that? A silly problem here. All right, you guys remember your order of operations? Okay. So let's try this. We'll do we'll say this is 12.0 millimeters by 8.2 millimeters, and then we're going to add another piece here. 4 millimeters by 4.2 millimeters. What is the total area of the two shapes, two pieces? Oh, parentheses, exponents, multiplication. Huh? Multiplication, division, multiplication and division go together, and then addition, subtraction.
There was one aside, please excuse my dear and Sally.
Yeah. That's how we remember this. Okay, what are we reporting to here? Do we get that? No? Maybe? Okay, well let's see. Let's break this down. Okay. What is the area of this thing? So you do 12.0 times 8.2, you get 98.4 millimeters squared, right? But we have to report down to two significant digits because we're doing multiplication. So we get 98 millimeters square, or square millimeters. Okay, over here, what do we have?
16.8.
Yeah, 4.2 times 4 millimeters, so we get 16.8 millimeters square. But we have to go down to
16.
uh,
You have
one significant digit because of the 4 millimeters, right?
yeah.
So that will be what?
16.
20 millimeters square, right? 20. One digit. Do we have that? Because it's multiplication, right? So multiplication, you do the number of significant digits, and we have one digit over here, and over here we have two digits. So our final answer has to have one digit, right? Okay.
You came up with the 20.
Yeah, okay. Okay, so 16.8 rounded down to one digit. I'm going to have just one digit being significant. So should it be, so I look at the number that comes after the ones, or the tens place, and it's a 6. So that means I round up to 2, right? So I'm going to have 20 millimeters squared because I'm rounding to one digit, so I'm looking at this digit, and that's a 6, which means I go up to 20. Okay, so I have 20 millimeters square here, okay? Now, in terms of, we're looking at decimal places, okay? And again, this is, if we had to, I don't know, turn this into another unit or something else. So we might say, okay, well, we'll do 98 plus 20 and we'll get 118, okay? But because this is accurate, so I don't know if decimal places was the right word to use, but I don't know. It is decimal places, but this is accurate only to the tens place, okay? It's not accurate to the ones because there's only one digit that's significant. So it's accurate only to the tens place. So our final answer should only be accurate to the tens place when we do the addition rules. Okay, so this answer over here, when we do the addition rules, is accurate to the ones place. And this over here is accurate to the tens place. So our final answer has to be accurate only to the tens place. So we do 98. Let me choose the other color. 98. Okay, so or significant up to the tens, ones place. And 20 significant to the tens place. We add those two together, we get 118, but our final answer should is significant only to the tens place. because of the rules of addition. So we go to 120 millimeters square. Yes.
I'm still confused.
Okay. I know. I expect everybody to be a little bit hating this.
You know why? Because 4 by 5 gives you 20. 4 by 4.2.
I know. Okay.
By the rules, it does.
By the rules, it does give you 20, and by the rules, we should only report accurate to the tens place. I know. It feels.
Building a house, that's not going to fly.
Yeah, go ahead.
I'd just like to explain where I'm confused. Maybe
Oh.
that might help you.
Yeah.
In clarifying it for me.
Okay.
So with the with 20, it's accurate to 2.0, right? So it's like so it's 98.
So.
Okay,
Yeah.
Okay, the problem is 98. I see it as 98 point plus 2.0, and then when we add that, it's 118. And then when I'm thinking according to the laws of significant figures for addition, it's to the least amount of decimal places. I'm thinking the answer should be 1.0 times 10 to 2.
Okay, so you're thinking it should be 100 and not 120. Let me think.
I think for the same reason I would say 16.8.
It's the least amount of decimal places.
Okay, so I guess it should be to. So when we think of the decimal places, I guess we're used to thinking of places after the decimal, like the tenths and the hundredths and the thousandths and things like that. But technically, a decimal place is also the ones, the tens, and hundreds. Okay, and so when you're doing addition, okay, if we say something, you have a 50-pound bag of potatoes or whatever it might be, that's technically only accurate up to the tens place. Okay, because if if it's just 50, it could actually be 51 pounds or 52 pounds or something, unless somebody says it's 50 point, and they put the decimal in there to signify it's accurate to the ones place. Okay, and so in our case, this is technically. I understand what you're saying. You are saying it is 2.0 times 10 to the 1. Okay, so in terms of decimal places, this is accurate to the tens place. Are we in agreement there? Okay, so we are accurate to the tens place. It's not the hundreds place. So we're accurate to the tens place, and over here we're accurate to the ones place. So when we add those two together, we're accurate to the tens place. Maybe we'll just do a few more examples, and we'll do this after lunch.
Okay.
Just to make sure. No, it's and don't feel bad, because it goes against what everything you feel like should be correct, right? Part of you says, part of us wants to be as precise as we can, but we have to recognize that if you have one measurement in there that's just kind of inaccurate, or not inaccurate's not the right word, imprecise, or it contains a great deal of uncertainty, it doesn't make sense to go on. Okay, and so Bradley, you were talking about building a house that's not going to fly, and the truth is yes, if you have pieces in your house where the measurements are not done well, and there's a lot of uncertainty in the measurement that you're receiving, your house is there's a lot of uncertainty you're dealing with. So when you make measurements and you cut your lumber or whatever you want it to be, you want to make sure that they're within a certain amount of tolerance and they're accurate, right? If you say, when you say I need a piece of wood that's 10 feet long, it's not give me a piece of wood that's 10 feet. You're saying essentially I need a piece of wood that's exactly 10 feet long. You're asking for 10 point at least 00 feet or 10.0, something like that. You want it to be accurate to the at least to the nearest eighth of an inch or something. So there's an implicit amount of precision specified. If somebody gives you back a piece of wood that's 9 feet long, okay, or 9.5 feet long, it's off by 6 inches, and they say, this is close enough to 10 feet, and you try to use that as your house is going to be all messed up, okay? And so if the measurements are bad, it's gonna propagate problems. And so we should recognize that having only one significant thing, this means that essentially this one and only digit was eyeballed. Okay, because you're supposed to use all the decimal or measurements that and then that last digit is eyeballed, and to have only one significant digit there means that digit was just eyeballed. I'm just looking, yeah, that looks like it's this tile right here. It looks like it's 2 feet across or something like that. And then and then if I were to use this to try to make a map or something, we're gonna run into problems because I'm just looking at it and eyeballing. So yes.
Could you just give me the 98 in scientific notation?
So the 98 would be, yeah, in scientific notation would be 9.8 times 10 to the 1. And then over here, this would be, so actually, it's not 2.0, it's just 2 times 10 to the 1. Okay? And then so when we add these up, we get 11.8 times 10 to the 1. And then because we're accurate only to the tens place, so I should get rid of that over here. We end up at 12 times 10 to the 1, or 120. We'll do some more. We'll do some more exercises. Okay.
That helps much more.
Yeah.
Does that help?
Yeah.
That makes
Okay.
much more sense.
Okay. I'm glad. Just changing it a tiny bit makes more sense. So is it lunchtime? Like in a few minutes? All right. Am I allowed to just let you guys go a little early for lunch? Okay. All right. I don't know. I don't want to get in trouble or anything. Okay. So yeah. Okay. We'll